In this lecture, we are going to see about electromagnetic waves, the nature of electromagnetic waves that arises out of Maxwell's equation. So, I'll use the pointer tool now. So, you recognize that this is the wave equation, and we'll compare it with the wave equations for E and B that we derived using Maxwell's equations now. So, what we do is we take the curl of the third Maxwell's equation, and which is Faraday's law. And when we do that, okay, so here you see doing that, and this is the identity. So this is the curl of E is actually uh, this expression. Okay, this is a formula, vector calculus formula. And when you do that, we know that del dot E is equal to 0 because we are talking about in regions of space where there is no charge. Okay, we're talking about Maxwell's equations where there is no charge. So del dot E is 0. Okay, and then what we do is we know that E can be written as, so this del cross E can now be written out as, you can see del cross E. What is del cross E? Minus dV by dt. So we write this expression on the left as del cross minus dV by dt. Now we just take the del inside. And now, as I told you, we apply the term that del dot E, we equate this expression here. Okay, let me point it out. We equate the one I'm pointing out with the one I'm pointing out right there. Okay. Now del dot E is 0 because by virtue of Maxwell's equation here del dot E is 0. Okay, so what you would eventually get is this equation. You would get this equation. Okay, so similarly for when you take the curl of uh, del cross B, the fourth Maxwell's equation, Ampere's law, what you would get is this. Okay, so here the derivation is on a similar process. You would get this equation. So what you've essentially got is, you get this equation. So what we've essentially got is a wave equation. So you compare it with this equation here. Compare it with this equation here. You have got a wave equation for E and B. And if you compare the equations, you can see now here 1 by v square is the velocity. Okay, velocity square. So what you have in that place is mu naught by mu naught epsilon naught. So v is equal to 1 by square root of mu naught epsilon naught, and that gives the value of the velocity of the speed of light or speed of electromagnetic radiation in vacuum. So you can see that it is theoretically got here as 3 into 10 power 8 meter per second. Okay, okay. So now the solutions to these, so these are differential equations, right? Second order differential equations. So the solutions are, we can take the solutions to be this form where k is actually a wave number. Okay, k is a wave number. We'll essentially make it into a vector now eventually, but k is a wave number and it is given by, it is related to wavelength in this way. K is equal to 2 pi lambda. Okay, k is equal to 2 pi lambda, and z is the, so z is where the electric field is varying. Z is the direction in which the electric field, the z is the direction of propagation. Okay, z is the direction of propagation, and electric field is a function of z and t. Okay, and this omega is the, so this omega is the angular frequency, right? Is the angular frequency. So and t is this time. Okay, omega is angular frequency and t is this time. Now we apply additional, now on these solutions there are some additional constraints applied by Maxwell's equation such that the resulting solutions are of this form that is given here. Okay, so we can write it out this way, resulting solutions, and here this n cap is the denotes the plane of polarization. This is the unit normal. N is the there is a unit normal to the plane of polarization, and it denotes the plane of polarization or the direction of polarization of this light. And here k is made into a vector. Okay, k dot r, k is a vector now, and k is called the propagation vector. It denotes the direction of propagation, and it's dotted with the position vector or the or r, right? So it picks out. So essentially, you get back this kz. Okay, you get back this kz, and we have omega t, and the vector b is related to e this way. Okay, where we have the k, the propagation vector. So this is the direction of propagation. So this is what talks about the transverse nature of electromagnetic radiation, that all these three vectors are mutually perpendicular. So k is perpendicular to e, okay, and the cross product of these two are the cross product of these two, which is b, is perpendicular to both these two vectors. So there are three mutually perpendicular vectors, and here the 1 by c denotes that the magnitude of b is very much less than that of e, okay, by 1 by c times. Okay, so once you find e vector for any wave, you can just take the cross product with k vector, the propagation vector, divided by c to get the b vector, or the magnetic field, how the magnetic field varies. So here you can see the full equations written out.